Good day, everyone. Yeah, welcome back to Ray class. And my name remains Engineer Shegun. And today we'll be looking at EMF, loss voltage, and the terminal voltage of a cell. It's important for us to know that a cell is an electronic device or an electrical device that converts chemical energy to electrical energy. And we should also know that there are two types of cells. There's a primary cell and there's a secondary cell. A primary cell is that cell that cannot be recharged. That's the basic thing. But you can make it look more complicated by saying that a primary cell is that cell whose chemical process that is producing the electricity cannot be reversed by putting current in the opposite direction to the current that they produced. Secondary cell, on the other hand, are those cells that can be recharged. In other words, the chemical processes that is producing the current can be reversed by putting current in the opposite direction to the current that they produced. Now, that being said, every cell has an internal resistance. And what do we mean by EMF? The full meaning of EMF is electromotive force. And the electromotive force is the total potential difference across the terminal of the cell when it is not delivering current to an external circuit. We could also say that electromotive force is the total work done per charge, not just work done, but work done per charge, per positive charge, in driving a unit positive charge around a complete circuit, and that is electromotive force. So, a cell, when it's not in use, has an EMF, that is the total potential difference across the terminal. But like I said, every cell has an internal resistance. So part of that EMF will be lost, not everything that can be used because of the internal resistance that it has. So I can say therefore that if I have a cell E, let's say the EMF of the cell is E, and then the voltage that is lost due to the internal resistance, let's call it VL, the loss voltage. So I'll say E minus VL. And what is left is known as the terminal voltage, which is VT. Now, remember that that cell is connected to an external load or an external circuit or something. So I have E. My loss voltage is actually current times the internal resistance of the cell. While the terminal voltage can also be current times the external resistance. From here, I can make an I subject to formula if I want. But what is most interesting here is that if you are asked to calculate for the loss voltage, just know that VL is your loss voltage and loss voltage is the current times the internal resistance. The current that the cell is producing times the internal resistance, that is the loss voltage. And the terminal voltage is IR, where R is your external resistance. So if I make R subject to the formula here, or if I take this guy over to this side, this minus IR over to this side, I'll have E is equals to IR plus IR. Now, if you observe this thing closely, a student will want to memorize this. But once again, there's no point, there's no need to memorize this stuff. Because if you remember Ohm's law, which we initially said that Ohm's law is V is equals to IR. Look at this both stuff. I can factorize this guy, and I can have E is equals to I into R plus R. Now, you will notice that R plus R is one big resistance. It simply means I'm combining or adding the external resistance to the internal resistance. It's still nonetheless resistance, just like this one is resistance. So if you know Ohm's law, this is still Ohm's law. Alright? Now if I make current I, so with the formula here, I'll have I to be equals to E over R plus small letter R. And this is a very important equation. As a matter of fact, this is important to understand this concept. Then this one led us to this, and this led us to this. But this particular equation does not need to be memorized. Once you know Ohm's law, you can always get this. And this led us to this. Of course, again, from Ohm's law, V is equals to IR. If I make I subject from now, I have I is equals to V over R. This resistance, just that this R plus R is the total resistance of this. The next thing I would like us to look at is how we can arrange cells. Cells can be arranged in series and cells can be arranged in parallels. In series arrangement, It means that for series arrangement, I have the positive terminal. This longer part is the positive terminal of the cell, while the shorter part is the negative terminal. Connected to the positive terminal is connected to a negative terminal, and that negative terminal is connected to, and that negative terminal, then I have the positive terminal of that same cell connected to the negative terminal of the other cell, and so on and so forth. This is series arrangement. Now, there are three cells here: E1, E2, and then E3. If I connect them in series, the total EMF of the cells combined is the summation of their individual EMF. So my total EMF, E total, will be equal to E1 plus E2 plus E3. However, what will happen if I connect the cell in parallel? At this level, we'll be looking at identical cells. I want to say identical cells will mean cells that have the same EMF and the same internal resistance. Means they are basically built of the same material. So if I have identical cells that are connected in parallel, this is interesting thing that you're going to notice. If I have identical cells connected in parallel, and this is how I will connect the cells in parallel. All the positive terminals of the cell will be connected to a fixed point, while all the negative terminals of the cells will be connected to a fixed point. Then, of course, you can connect this to your load. All the positive terminals together and all the negative terminals together. This is a parallel arrangement. Let's say these cells are identical. So the EMF of this one is E, the EMF of this one will be E. The EMF of the combination of these cells connected in parallel will be equal to the EMF of just one of them, which is equals to E. That's interesting about connecting them in parallel. If I connect the cells in parallel, the EMF stays the same. So if this one of them was 12 volts, and I have another 12 volts, 12 volt, 12 volt connected in parallel, the entire combination will be 12 volts. But just that, the batteries will last longer for a particular load if they are connected in parallel. But if they are connected in series, the EMF will be building up. So if this were to be 12 volt, 12 volt, let's say it was just 12 volt, 12 volt connected in series, it should now be 24 volts. So that is the interesting thing about arranging them in series and parallel. So there are situations whereby you will need to arrange them in series, whereby there are situations whereby you need to arrange them in parallel, depending on what your goal is. Now, having said this, and having said this, the next thing I would like us to look at are some questions that they have asked based on cells around these areas. Now, still on EMF and loss voltage and terminal voltage, let's take our first question on that. So we have a cell in this question. The question says a cell of EMF 1.2 volts and internal resistance 1.5 volts, 1.5 ohms is connected in series with an ammeter of resistance 0.5 ohms and a load of resistance 4 ohms. The current in the circuit is, now they are asking us for the current in the circuit. Well, the first thing that now we go to is that I know that the current in the circuit here, they are giving me the EMF, they are giving me external resistance, and they are giving me internal resistance. So basically, I know my formula will be current I is equals to E over R plus R, where R is the external resistance and small letter R is the internal resistance. I don't have a problem in knowing the internal resistance because they gave me the internal resistance of the cell. But there is a problem. It was two external stuff that was there. We had an ammeter and then of course we had a load. The ammeter had a resistance of 0.5 ohms while the load has a resistance of 4 ohms. So both of them were my external resistance and they are in series. So I will say that the external resistance R, because they are in series, remember that we have said before in the past that if they are in series, resistors in series, we just add them up. So the ammeter is 0.5 ohms connected in series with the load, which is also in 4 ohms. So 0.5 plus 4 will give me 4.5 ohms. That is my total resistance. The next thing here is, I know my internal resistance obviously in the question, and the internal resistance of the cell is 1.5 ohms. Using my equation, I will have I to be equals to, the EMF like they said was 1.2 divided by the external resistance will now be 4.5 plus my internal resistance, which is of this cell is 1.5. Now, if I add this guy up, I'll have 1.2 divided by 4.5 plus 1.5 will give us 6. This is the same thing as simply saying what 12 times 10 to the power minus 1 divided by 6. And this is the same thing as saying 6 goes into 12 is 2 times 10 to the power minus 1. That is basically just 0.2 amperes as the current flowing in the external circuit. 0.2 amperes is the same thing as saying 0.20, and that's option A in this question. Now let's look at the second question. Still on cells, this is question number 2. Now this question is actually interesting because it will help me to explain some tricky aspects of the arrangement of cells. Now in this question, we have 3 cells, each of EMF 1.1 volts and internal resistance 2 ohms are connected in parallel across a 3 ohms resistor. The current in the resistor is, that's simply asking for the current flowing through the resistor. Again, we have internal resistance, we have the external resistance, and we are looking for the current. Our mind will simply go to I is equals to E over R plus R. But the next question we are going to ask ourselves is this. There are 3 cells, not 1, and they are connected in parallel. Just like I said earlier, if we have cells connected in parallel, then the EMF of the combination is just the EMF of one of them. That is true. So I know that my EMF E here is going to be equal to the EMF of the cell, which is 1.1 volts. Of the 3 of them, because they are all connected in parallel, then the EMF of all of them combined will be 1.1. The next question will now be, will the internal resistance R still be equal to 2 ohms? The answer is no. Although the EMF is 1.1, but the internal resistance, because they are connected in parallel, the internal resistance I need to calculate for it. And how would I do that calculation? So, when it comes to the internal resistance, I'm treating the cell like I will treat resistors. And if resistors are connected in parallel, we know how we will add them. So that means I'm having 1 over R total is equal to 1 over R plus 1 over R plus 1 over R. Note, I'm not doing 1 over R1 plus 1 over R2 plus 1 over R3. The reason why I'm not doing that is because I know that the cells are identical, their internal resistance is the same. So I go to R. Now, if you watch what I'm going to do from here, you will notice that this is what I will do. R total will now be equals to all these guys, R are the same. I can just pick one. In fractions, if the denominators are the same, I'll pick one. So I'll just get R. Add up all the numbers in front, which is 1 plus 1 plus 1 plus 1. That will give me 3. If I turn this thing around because I'm looking for R total, then I'll have R total will be equal to R divided by 3. So if you have 3 resistors arranged in series, arranged in parallel rather, or 3 cells arranged in parallel, and I'm looking for the internal resistance of that combination, it will be R divided by 3. If it's 4, it will be R divided by 4. If it's 5, it will be R divided by 5. That means if it's N cells in parallel, then the total internal resistance will be R divided by N. But by the way, what is R? R is 2. So that means I'm having 2 divided by 3. I know my internal resistance now. So let's go ahead and solve for our currents. So solving for the current, I'm going to have I is equal to EMF is 1.1. The external resistor, it was connected to an external resistor of 3 ohms. Raised 3 will be 3 plus my R total I'll be using here is 2 over 3. Now I can simplify this whole stuff. This is I current. So I can simplify this whole stuff as 1.1 all over. And there's a simple trick I can use here. This is the same thing as over 1. So I can just do 3 times 3 1 times 2, 1 times 3. So this will give me 9 plus 2 over 3. So which of course I can break down as 1.1 over 9 plus 2 is 11 all over 3. This is the same thing as saying 1.1 divided by 11 over 3. And this is the same thing as saying 1.1 times 3 over 11. Well, this is not the same thing as saying 1 times 10 raised to the power minus 1 times 3 over 11. Well, these all stuff are just simple algebra, and I'm doing it without a calculator. You can easily use your calculator and you get your answer straight. So this whole stuff here shouldn't confuse you. Then from here, what I'm going to have is this 11 becomes what is 11. Then I'm going to now have 3 times 10 raised to the power minus 1, which is simply as saying 0.3 amperes as my current. 0.3 amperes, which is option B. So the interesting thing that I wanted you to notice is how I got the total internal resistance of the 3 cells connected in parallel. If there were 3 cells connected in series, I would have added up their EMF. Then I would also add up the internal resistance to get my RO total. So that in this equation, the RO I will be using here, if there are multiple cells, will be the RO total, the small letter R, and of course I know my internal resistance. So have that in mind if you are solving questions like this, and it will be very easy to solve any question around these areas.